Hello everybody, my name is Mohamed Idrisi. I'm from University Sid Mohammed Abdullah. Today I will present our work titled An Improved Smart Wheat Health Monitor for Smart Farming Application using Deep Residual Learning Framework. So in my presentation I will follow this plan. First of all, I will give you an introduction. Next, I will expose the purposes of our work. Next slide will be a brief comparison between shallow planar network model, deep planar network model, and ResNet plan model in terms of many criteria that we'll discover later. After that, deep ResNet learning framework will be presented, followed by smart with health monitor model conception. Later, I will present some of our findings and use case. And finally, I will close my presentation with perspectives and references that I mentioned in the slides. So, the global topic of our work is smart farming or smart agriculture. It is seen as one of the most domains that have taken benefits from technologies in all of its processes. These technologies includes Internet of Things and machine learning. Another reason of our contribution is the widespread of bioagri-source that treat the wheat crops with health monitoring, what makes the productivity minimized. These reasons, among others, make classical wheat crops health monitoring very difficult and very hard and very tedious for traditional farmers. So this work applied ResNet framework to build an automated framework to help farmers to monitor their plant health uh, in their daily tasks. Now, what are the main contributions of our work? This slide gives the answer. We try throughout this work to improve the metrics of our previous work, such as maximization of accuracy of classification, minimization of error rates, as well as optimization of the time of training using the technique of random elimination of blocks of neural networks. Another purpose is to conceive a deep neural network without worry about complexity or vanishing gradient problem based on convolutional neural network. Actually, vanishing gradient problem is an issue that can be occurred because of multiple derivation of the optimization function during training process. Now, this slide gives us a comparison between three types of neural network models: shallow plan neural network model, deep plan neural network model, and ResNet model in terms of number of layers, accuracy, error rates, architecture flow, time needed for training operation, and generated complexity. The criteria that interests us is the architecture flow. It means how many paths the model has. The two types of plan models contain only one main path. However, in ResNet model, we find two paths, main and shortcuts. These two paths define also two kinds of building blocks that we will discover them in the next slides. So here we have the ResNet building block. As we said earlier, it consists of two paths, main path and shortcut. The shortcut transmits the signal in the input of one or more layers to the output of one or more layers. This is what we call identity mapping between the input and the output of a certain number of layers without adding any extra parameters or network complexity. The output fx of the skipped block of layers is simply added to its input x. This option is very important because it allows to the previous layers to contribute to the activation of the later layers, as well as the gradient is always there. There is no gradient variation phenomenon when the model is trained by back propagation. So as we said in the comparison slide, there are two types of ResNet blocks, identity and convolutional building blocks. The difference between these two types is the shortcut path of the block. in the identity block, there is only one identity mapping between the input and the output of the skipped layer. We use especially this type when we have the same features, dimensions of the input and the output of the skipped block of layers. But when there are different dimensions, we adopt the situation using a block of 2D convolution and batch normalization. The add function will be possible in this case. The output of each ResNet block is passed through a RULU activation function. RULU, it means rectified linear unit activation function. Now let's move to talk about the conception of our smart with health monitor. This is the physical architecture. It basically contains the essential elements of a machine learning model. The data set that we use to test and validate the model is CGIAR computer vision for crop diseases. It is referenced in the reference slide. We divide it into four subsets using cross-validation technique. Three of them are used for training, one for validation. So the test subset is acquired from the field using our own camera. The model is trained on a cluster of 8 Cisco UCS nodes. UCS, Unified Computing System nodes. Each node has 256 gigabytes of RAM. So right now, this is the Smart with Health Monitor logical architecture. Here we define what we call stages. Each stage is consisted of identity and convolutional ResNet building blocks. The model contains 7 stages deep. We increase the number of building blocks and the size of the mask called also filter or kernel used by conv2D function in each stage. The couple conv building block, identity building block used in each stage successively are 1, 2, 1, 3, 1, 5, 1, 7, 1, 9, and 1, 2. The first stage contains only a simple conv2D function. A dropout function is used at the end of the model to avoid the overfitting problem. So the model now is built, and this is the algorithm used for training process. The training subsets is composed of RGB images of healthy and infected with crops with multiple kinds of diseases. We first define the hyperparameters like steps, batch size, training ratio, and the size of targets of image in pixels. The process begins with the definition of data propagation strategy, followed by data augmentation strategy. Next, the identity and convolution blocks are defined. We next map the model. We calculate the number of steps by epoch, which depends on the number of samples in each operation, the batch size, and the ratio. The algorithm monitors the accuracy matrix. It means if there is no changes in its value, the early stopping function is executed as the training process continues executing. So now this is the loss and the accuracy function that we got after 100 epochs when they are over. So we got loss and accuracy curves. The accuracy function continued increasing till the epoch number 60, where it basically flattens. The loss function varies propositionally reversed. So this slide shows us some of our findings. They are used to evaluate the conceived model. In the figure in the left side, we injected eating images that are previously labeled as infected and healthy. The model can predict each one of them exactly as it was expected, with a certain accuracy. In the right side, the confusion matrix of 18 test images. From the confusion matrix, we can extract the following evaluation parameters. Accuracy, for example, is improved to 83.33%. The error rate was decreased to 16.67%. The sensitivity or true positive rate is 88.88%. The specificity or true negative rate is 77.77%. So this slide summarizes the enhanced matrix regarding the previous values. For example, precision of detection is increased, as we said, to 83.33% from 80%. The error rate was decreased from 20% to 60.67%. The ROC value also was increased from 75% to 93%. Here we have an example of four-step scenario where the model can be implemented. As we see in the figure, a network of sensors are installed in the field to collect data about environment variables such as humidity, temperature, soil moisture, etc. A CCTV camera are also installed in the field to take real-time pictures to the crops and transmits it wirelessly to fog computing layer where the model is implemented and executed. When the decision is made by the system, it is then notified to the farmer control system, which can be, for example, a web application or mobile alert notification system. The farmer can intervene if it is required. So to conclude, I say that our work applied ResNet framework to build a wheat plant health monitoring system in order to help farmers in taking decisions about their wheat crops and improve their productivity. The metrics that we improved in this work are accuracy of detection, error rates, or crop value using a very deep neural network with minimal complexity. So as perspectives, the next step will be to take into account the random elimination method to randomly switch off some of the model blocks. Thus, the training process will not take a lot of time. From another hand, we are working on a smart farming system composed of three modules: plant health monitoring, smart irrigation forecasting system, and smart blender to optimize the quantity of fertilizers required by the crops. This is the first module. There are modules. The other modules are coming. Here we have the references that we mentioned in the presentation. Number one is our previous work. It is now under review in Sustainable Computing, Informatics, and System Journals. Number two refers to data set that we use to train our model. Finally, thank you for watching. If you have any further questions, please email me at mohammed.elidrisi29@usmba.ac.ma. I repeat, mohammed.elidrisi29@usmba.ac.ma. And thank you again for watching.